Okay. So this session is recorded and it will be available on the IEEE YouTube. It will be posted after. Okay, so hi, welcome to the Electronics 1 ELG2136 Cookies and Cram. I'm Michal. I'm a fifth-year electrical engineering and computing technology student. So I took this course 3 years ago. So disclaimer right off the bat, I'm not a professor, I'm not a TA for this course, but I am gonna try and review and help you guys out to get ready for your exam, which I believe is this Friday, I think is what I heard. I might be completely wrong. But it's coming up soon. So the outline for today, I have 3 questions from the textbook that I want to. Oh, what exactly are you like? Why do you run these things? So IEEE runs Cookies and Cram, so review sessions for first and second year engineering courses each semester. So we ran them in the fall, in December, and we're running them now for the winter semester. So I've been involved with IEEE for 3 years. This year I'm the chair, and I usually run or help run the ELG Cookies and Cram. So I like to help out because I know I definitely got help and review from people when I was taking these courses. So I like to give back and help you guys as much as I can. So the schedule for today, like I said, we have 3 questions that I'd like to go through. I think we can get through them in an hour. And at the end, we'll have a Kahoot. And the person that wins the Kahoot gets a $5 Amazon gift card. So that's because usually we have it's called Cookies and Cram. Usually if we were doing it in person, we'd have cookies and be a great time. But unfortunately, we're doing this online now. So Kahoot it is. All right. So if you guys ever feel like you want me to go faster, slower, explain something, skip things, just let me know. You can unmute yourselves or you can write in the chat, whichever one. So this first question, I'm going to be focusing on the second half. So that's BJTs. Yes, it is being recorded. Yeah. So I'll be focusing more on BJTs and MOSFETs and AC analysis. Oh, there's some people. Yeah, so we'll start with 6.66. These are all questions from your textbook, so you can find them if you need to. So this is the circuit. Let me just read out the question. It says, for the circuit shown, find the labeled node voltages for beta A. Beta is infinity, and B is 100. So I will start here. I will just start working through them with you guys, kind of what you need to do. An important thing to remember for this course, and I think I saw somebody say that there's actually not that much material. It's just, it can get overwhelming because there's so much. Like it feels like there's so many different problems, but what you really have to remember is there's a few steps you need to do, and you just always have to think through them and just do them. There's actually not that much, just as long as you are working step by step. So for this first one, okay, we have beta equals infinity. So from this, we know that that means that the current at the base, IB, is around 0. So what I like to do at the beginning is always write out all the things that I know. So we know that IC is equal to beta IB, which means that it's around 0. Sorry, that is not correct. It's not around 0. so we have beta equals IB. Now we have that IE is beta plus 1 IB. And we know that IE is equal to IB plus IC. So since IB can be said that it's 0, we can say that IE is around equivalent to IC. Okay. Oops.
Thank you for bringing me my water.
We're going to start with finding V1. So V1 is right at the base of Q1. So we know that V1 is equal to, okay, so I'm saying IB1, that's from Q1, times the, so that's what's going into the base there of the Q1 BJT, sorry, my bad, and times 100K. And we know that IB is around 0, so we can say 0. So from that, and that's our VB1, and so we can say that V1 is equal to 0. Yes, okay. Moving on to VE1. So that's the voltage at the emitter of Q1. So that's VB1 plus our 0.7 volts. So it's a pretty easy calculation. We get that V2, which is VE1, as we can see labeled up here, is 0.7 volts. Okay, so now we're going to find the current at IE1. So the emitter current. So we're going to do a node voltage. We have 3 volts up there. 3 volts minus V2, which is our VE1. And we divide by the 9.1K resistor. And from that, we get 0.253 milliamps. So since we know from the beginning, from what we wrote up here, we know that IE is around IC. We can say that they're equal. So then we know that IC1 is also 0.253 milliamps. So now we can find IC. Again, it's the same procedure. You just do your node voltage, which is V3. V3 is, let me scroll up so you guys can see, is right here at the collector. So it's VC1. It's also VB2. So V3, and then we do minus, and we have a negative 3 volts at the bottom. And we divide it all over our 9.1K resistor. So from this, we can, after subbing things in, I won't do the math here, but if you're ever confused, let me know. I recommend, I always say this, but on exams and assignments and whenever you're doing work, don't skip steps, even if you're doing it in your head, even if you're doing it on your calculator, try and write them all out. Yeah, try to write all of your steps out so that you won't be confused and you're able to go back through them. Okay. Right. So now we know that VB2, so that's our voltage at the base of the second transistor, is the same as V3. And so now we're going to find VE2. So that's V4, which is the voltage at the emitter of our second transistor. VE2 is just VB2 minus 0.7 volts. So that's just something we know about the BJT in active mode. So from that, we get that V4 is 1.4 volts. Okay. So we now find IE2 so that we can move up to the collector. So IE2 is V4 minus -3 volts over our 4.3K resistor, which gives us 0.372 milliamps. All right. Moving on. Okay, so again, we know that IC2 is around IE2. So from that, we can get that IC2 is also 0.372 milliamps. IC2, so this is our, again, current through the collector and the second transistor. We can write, we're trying to find our last node voltage, which is V5, which is the VC2. So we write 3 minus V5 divided by our 5.1K resistor. And from this, we're going to get that V5 is equal to 1.1028 volts. So we can see that when beta is equal to infinity, it's a little bit easier. Our task is a little bit simplified. So now we're going to do B, which is when beta is equal to 100. So this is a little bit more complicated. Mainly it's just the math that's complicated. It's not actually any harder. You're still just writing all of the same, all of the equations out that you know, just going step by step. So we're gonna again write out everything that we know given this information. So we know that IC is equal to 100 IB. We know that IE is equal to 101 IB. And we also know that IE is equal to IC plus IB. Okay, so let's write this out. V1, as we know from before, is VB1, which we can write as IB1 times our 100K resistor, which we can also write as 100K times IE1 over 101, just subbing in the equation we have right here. Okay, so now we're going to write our equation. Oh, perfect, thank you for letting me know. I've let them in. Okay, so now we're going to write our equation for VE1. Actually, I have big writing, so I'm going to move to a new line so we have room. So VE1 is VB1 plus our 0.7 volts, right? So we have 100K times IE1 over 101 plus 0.7 volts. Cool. So moving down, we can also say that IE1, so another thing that we know, right? So we're finding IE1, we can do our node voltage, 3 volts minus VE1, which we have an equation for, and we divide by 9.1K. All right, so rearranging this, let me see if I want to write all of this out just so I'm not mindlessly writing. Yeah, basically, when you sub everything in, you're going to sub this VE1 in. So you're going to get that IE1 is equal to 2.3 volts divided by 9.1K plus our 100K divided by 101. And this is going to get a 0.228 milliamps. Does that make sense to everybody how we got that? It's really just math and rearranging, but let me know if ever something doesn't make sense or if you want me to go faster. Okay, so now we're going to find V1 since now we have our IE1. So this is the equation we had. IE1. And so subbing that in, we get V1 is 0.226 volts. Cool, so we have this voltage now. Now we're going to move on to our V2, which is going to scroll up to this. V2 is our emitter voltage at Q1. So V2 is just V1 plus 0.7 volts. Again, we are assuming active mode always when we do these. And then I guess at the end you want to check that that was correct, that your assumption was correct. V2 then is 0.926 volts. Okay. So now we're going to find our IC1 so that we can find our V3, which is at our collector for this first transistor. So IC1, again, we know that it's 100 IB1, which is the same as 100 IE1 over 101. And so we can sub that in and we got 0.226 milliamps. All right, and then another equation for IC1 that we can write so that we can find V3 is V3 minus negative 3 volts divided by 9.1K. And isolating, we get that V3 is equal to 9.1K IC1 minus 3 volts, and so we get that V3 is equal to negative 0.943 volts. Okay, that makes sense. Now we're going to move on to V4, which is the emitter of Q2. So again, we know that V3 is the same as VB2. And we know that VE2 is equal to VB2 minus 0.7 volts. So we get that V4, which is VE2. I'll write that out actually, so it's clear. V4 is negative 1.643 volts. Okay. And lastly, we are doing IC2, so, oh my bad, IE2, which is V4 minus 3 volts divided by 4.3K, and we get 0.316 milliamps. Okay, so then we know that IC2 is 100 over 101 IE2. So we get that 0.313 milliamps. We can also write the equation for IC2 as 3 volts minus V5 divided by 5.1K. So V5, again, is our voltage at the collector. And from this, we get that V5 is 1.4037 volts. All right, so that's the end of this question. The main work was always write out what you know and then try and write as many equations as you can to get from each node voltage to the next. So this was just a pure DC analysis. We're now going to go to a question that has AC analysis, which I think is the main thing you guys have been focused on in the second half of the course. So I'm going to read out this question and what we're given for it. So this is 7.33. Okay, so what problem was the last one? The last one was, let me get it, I think it was 6.66. Okay, so 7.33 says, it's a bit of a long paragraph, but I'll read it out. So this figure that I have here shows a discrete circuit amplifier. The input signal V sig is coupled to the gate through a very large capacitor shown as infinite. The transistor source is connected to ground at signal frequencies via a very large capacitor, also shown as infinite. The output voltage signal that develops at the drain is coupled to a load resistance via another very large capacitor, shown as infinite. All capacitors behave as short circuits for signals and as open circuits for DC, which is something I'm sure all of you know at this point. So question A asks, if the transistor has VT equals 1 volt, Kn is equal to 4 milliamp over volt squared. So this question is a verification. We're going to work through it as if they don't give us this information. I think it's more useful to you because I don't know that they will be giving you a question about verification. I mean, maybe. It's really good actually to work through it the other way because now you know the solution, you know what you should be getting. So we're going to do this. So we do our DC analysis. That's our part A. So that means we are going to open all of our capacitors. So we can redraw our circuit like this. This is 7K, this is 16K, this is 10M, and this is 5M. I'm going to label this as I1. This is also actually I1. This is our ID, and this is our IS, which is equal to ID. Okay, so what can we find? We want to find, what am I looking for in the end? We are looking for VGS and ID, as well as VD. So we're going to find those three. We're going to find VGS, VD, and ID. Okay. So we're going to start with what we know here at the top at ID. I should write, there's a plus 15 volts here. So that's where those two are going at the top, the two arrows. So we have ID is equal to 15 volts minus our VD, which is our voltage at the drain, over our 16K resistor. And just rearranging, we can get this equation. Okay. So now we can find I1. I1 is pretty easy to find because we have everything we need for it. I1 is our 15 volts divided by, if we make that loop, so that's really what it is, 10M plus 5M. So when you do that calculation, it's 1 microamp. And we can make another equation for I1. So this one was across both of the resistors, but what we can do is I1 15 volt is equal to 15 volts minus VG. So VG is right here, minus VG divided just by that first resistor of 10 mega ohms. So from this, we can isolate VG, and we're going to get that it's 5 volts. Okay, so now we're going to find what ID is, another equation for ID using VS. So VS is at the source. So because we're wanting to find VGS, we're going to need VS as well. So we get that ID, actually I should write it as IS, probably easier. I mean, IS is equal to ID, so let's do it like that. VS over 7K. That's the 7K resistor, so we get that VS is 7K ID. We're going to be using ID everywhere. ID and IS are equal, but it just makes it easier for our equations. Okay, so now we're finding VGS, or at least writing our first equation for VGS, because we can't actually find it yet, or like the value of it. So we have our VG minus VS, we have VG is 5 volts, and then our VS is 7K ID. And now we're moving on to ID. So we do have an equation for ID, just 1/2 Kn W over L, VGS minus VT squared. So W over L isn't given to us, so we are assuming that it is 1. So we're going to rewrite this as with our values. Beautiful. And so we end up with this as our equation for ID. So we can open this up. Let me, I won't show all of these calculations, but basically you're going to do this square, then you have to remember that you have an ID everywhere here, and to find your roots, so to find what ID is, it's going to open up to be a quadratic function. You're going to want to move that ID over. So actually I can write that out just so it's a little clearer. So we can have ID is equal to this. I don't know about you guys, I always use the I'm terrible at just doing it mentally, so I'm sure you guys know, but you can do the sort of this. When you're doing your square, right? And then fill those in, and that will give you this. But you want it to equal to 0, so you're going to subtract this one ID from this side. So you're going to get, don't know what happened there. You're going to get 0 is equal to 98 times 10 to the 3 ID squared minus 113 ID plus 0.032. Cool. So from this, using your quadratic function, which I'll write out, but I'm sure you guys have memorized. Okay. And we're going to find that we have 2 options for ID1, which is 0.653 milliamps, and ID2, which is 0.5 milliamps. So there's 2 things we want to check to make sure that we are in saturation. So I will write the 2 out. Let me just find what I'm looking for. VGS has to be, one sec, whoops. VGS has to be, oh, I'm still on eraser. VGS has to be greater than, no, it doesn't have to be greater than VT, my bad. That's not what I meant. VDS has to be greater than VGS minus VT, as we know, but also VGS, oh yes, that is what I want, right, is greater than VT. Oh, yes, thank you for letting me know. I didn't notice that. They are being admitted. Yes, I believe those are the two things we want to check. VGS is greater than VT, and that VDS is greater or equal to VGS minus VT. So let's check both of these. VGS is greater than VT. So VGS, we can now find, we have that equation, which is 5 volts minus 7K ID. And we can check for both of our IDs. So when we use ID 1, we get 0.429 volts. And when we use ID 2, we get 1.5 volts. So we can see that this is the ID we want because we need it to be greater than VT. VT, as we remember, is 1 volt. So this is less than 1 and this is greater than 1. So ID 2, so ID is equal to 0.5 milliamps is the one we're going to be going with, because that puts our MOSFETs in saturation. Okay, so now that we have our ID, so we found 2 out of 3 of the things we were asked to find. We were asked to find ID, VGS, and VD. So I'm actually going to write out what we know. I think this is a good practice. This is good practice for me. I didn't do this in my notes and I am struggling. You want to circle, I'm assuming you guys have a written exam that you scan in. It's a good idea if you have time when you get one of your answers, circle it, make it easier for the prof, make it easier for yourself to check your work as well. So ID is 0.5 milliamps, VGS, as we found, is 1.5 volts, and now we're finding VD. So we had that equation for VD, which was 15 volts minus 16K ID, and we find that VD is 7 volts. And you can check, this is what we were asked to verify in the part A of the question, so we did solve it correctly. Is there any questions before I move on to part B? I don't see any. Okay, so I will read part B of the question, which says find GM and RO given that VA is equal to 100 volts. So this one is fairly easy. We have all of the equations that we need. So we know that GM is equal to Kn over WL VGS minus VT. So let me quickly find that. Sub it in, and we get that GM is equal to 2 times 10 to the negative 3. Okay. And RO, again, a simple equation is VA over ID, which is 100 volts over 0.5 MA that we found. And that gives us that RO is 200 kilo ohms. So a little bit of an intermediary step that we need to do our AC analysis. But important to find, shouldn't be too difficult. Okay, part C. Draw a complete small signal equivalent circuit for the amplifier, assuming all capacitors behave as short circuits at signal frequencies. So we're going to draw a cute little circuit here. So this is our V sig here. And this is our R sig, which is 200K. This is VGS. Am I going to have enough room? No, I need to draw it smaller. Okay, like that. It's VGS. This is our 10 mega ohm resistor. So as you can see, it's now going to ground. So all of our DC sources are grounded. So our 15 volts no longer exists. We have this is our 5M. And this is the small signal of our MOSFET right here. So we're going to use the GM-VGS here. Oh, those are not really lined up. I'm so sorry. This is RO that we found. Then we have our two 16K resistors. And then here we have our VO. So this is 16K, 16K. This is also grounded. Am I missing something? Right. R sig is 200K. All right. And this is our plus minus VGS. VGS. And this is our RN. Okay. So does that make sense? You can see it's very nice to draw all of your grounds on the same side. It makes it easier to see which resistors are parallel. When I was taking this course, I didn't do this. I had like resistors flipped up and down, and it was hard for me to visualize this. It's a lot easier. So I recommend doing it like this. That might have just been me not being very smart about how I did things, but that is our small signal equivalent circuit. All right, so what does part D ask us to find? It says find R in VGS over V sig, VO over VGS, and VO over V sig. So again, I'm sure I've seen, I remember in my assignments, and I'm sure in your assignments, and maybe even, I don't know if you've had a practice final, something like that. I'm sure you've seen that you have circuits with like a MOSFETs and a BJT or multiple BJTs or multiple MOSFETs. But what you have to remember always is, again, write what you know, write all of your equations, do as many of the loops, nodal analysis as you can do, or the ones that you know will help you find what you need. At the end of the day, all of this is just writing equations and yeah, doing circuit theory. So slowly going through it. You can see Rn. What do we see? Like when you look in, you see this 10 mega ohm resistor, you see this 5 mega ohm resistor, and then you see this open circuit. So all you're going to see and say that, okay, Rn is 5 mega in parallel with 10 mega. And we get that Rn is 3.33 mega ohms. Something that's important. I don't know how your professors are with units. I've just been writing mega and kilo and milli, but you do want to be writing your full units. You want to be writing mega ohm. It's very important. Okay. Because I know sometimes profs can take off marks if you don't have your units in. Okay, so now we're going to find our next thing, which is VGS over V sig. So how do we write this? We have this here. Oops. I'm going to label as I in. So our current's going in. So if we redraw just the part that we're seeing, we have our, I have to keep going to the eraser. We have our V sig. We have our R sig here and our II going through. And then we have this RN. And this is our VGS right here, right? Does that make sense? So we can rewrite this pretty easily. We're going to get that II is V sig, R sig plus RN. Yes, so we can also write VGS over V sig. Oh, here, I'll skip this step, but I think I should write it out. Which means VGS is equal to VGS over RN, right? We're finding II or IN, however you want to say it. So we can find that it's got really ugly there. Okay, VGS over V sig is equal to RN over R sig plus RN. And when we do those calculations, we get that VGS over V sig is equal to 0.943. Remember, this doesn't have units because it's a voltage over a voltage. Okay. All right. So the next thing that we are finding is VO over VGS. So this is our V out. It's over here at the end of our circuit. All right. So how are we going to find that? First, we want to find what an equation for VO. So we can write VO. I wonder if I can. Okay, well, I'll scroll up here just so I can explain it. So VO, we see that we have, we want the current, right? It's the current at VO times our RO and our 216K resistors in parallel. But what is our current? It is negative GM VGS. Why is it negative? Because you think of your VO like that. It's a plus minus. So which way would the current be going? It would be going this way because our current goes from the plus to the from the positive to the negative, which is opposite of the way that GM VGS is going. As you can see, it's going down. This would be going up. So we can write our equation for VO as negative GM VGS times RO in parallel with our 216K resistors. And we know that both of those 16K resistors are in parallel. They're both connected to ground. As we said earlier, our DC sources are all grounded when we do AC analysis. Okay, now VO VGS, that helps us out because our VGSs write this out, are going to cross out. So what we're really going to have is, oh, I crossed out the wrong thing and wrote the wrong thing. Okay, I meant to write VGS. So we crossed out our VGSs. So now we just have negative GM, RO, parallel 16K, parallel 16K. And we have all of those values. So doing that math, we get that VO over VGS is equal to negative 15.384. And the last thing we were asked to find is VO over VSIG, which we can do using the two values we already have. We have VO over VGS, and we have VGS over VSIG. So we multiply those two numbers together, and we get a VO over VSIG is negative 14.507. Okay. Are we good with this? We'll leave this the end of this question. Does everything make sense? Does anybody have any questions about it before we move on to our last question? Okay, good. Okay. The last question I have ready here is 750. So this is a C analysis, but with a BJT. So a bit simpler. I think we can get it done, and then you can ask any questions, or we can go straight to a Kahoot. So let me just read out the question for you guys. 750. Okay. So this figure shows the circuits of an amplifier fed with a signal source VSIG with a source resistance RSIG. The bias circuitry is not shown. Replace the BJT with its hybrid pi equivalent. Find the input resistance Rin, which is V pi over IB, and the voltage transmission from source to amplifier input, which is V pi over VSIG. The voltage gain from base to collector, which is VO over V pi, and then we want to find the overall voltage gain VO over Vsig. All right, so first we are going to find our Rn. Okay, Rn, which is, oh, wait, yes, we're going to find, first we're going to draw our circuit actually, our small signal equivalent circuit. So we have our Vsig here, V signal, our Rsig, and now we're going to draw this one here. So this is here, they call it V pi, you can also call it VBE, but we are going to be using the beta IB equivalent here. We're going to be doing, as you know, there's two different equivalents. It kind of depends what you're given, what you're asked to find. This is our RC, and then we have our plus minus VO here. There's someone in the waiting room. Yes, I can. Perfect. Thank you for letting me know. All right. And then we have our RN, obviously, looking in here. Okay. Oh, and this is labeled as IB. Okay. So in this one, we aren't given any values, so we are going to end up with an equation with variables. But when you're choosing which small signal equivalent to use, obviously you would want to use beta IB, if you're given beta, if you know beta. If you're not given beta and you've had to find GM, you want to be using GMVB. So yeah, whichever one makes sense for the question you're doing. Okay, so we are first asked to find R in V pi, which is V pi over IB, which we can also see as we're looking in Rn, and what we're going to see is R pi, really. So yeah, so it's R pi. This again, we're not given numbers, so it will be just based on all of these variables. We're going to be finding the different equations that we would use. So it would just be R pi. In a question, you might be given values, and you can find R pi. So now we're also asked to find V. I think the next one was V. Let me check so I'm going in the right order as the question. I think the next one was V pi over V sig. Perfect. Okay. So we're going to do this analysis V pi over V sig. So V pi, we can see, this is what we're going to get. Again, this is very similar to what I drew for the other, for the last question, right? Because you have your V pi, which you can write as, if you redraw this, oh man, let me actually redraw it. Do I have to redraw? Maybe I can just write it out. Yeah, I'll just write it out. Okay. So you do that loop, you get minus V sig plus R sig IB plus V pi is equal to 0. Okay, so then you can rewrite this. You know that V pi is also equal to R pi times IB. So you get this, which is R sig. So you want to write the two equations for IB that you can get from these two. IB, you can say that it is V pi over R pi. And you can also say that IB is V sig minus V pi over R sig. So from this, we get this equation here, which is, actually, I don't know why I'm rewriting it since it's right here. We're going to rearrange, and we're going to get V pi over V sig is equal to R pi over R sig plus R pi. Okay. And the next thing we are finding is VO over V pi. So VO is, again, we want to find the equation for VO, which is, again, our current is going this way, so it's negative VIB times this resistor RC. and we divided by V pi. We can also rewrite this. Can we rewrite this? Yes, we can. To get rid of our IBs, so we can write that negative beta V pi over R pi is our IB times RC divided by V pi. So we're gonna cross out those, and what we're gonna get is that VO over V pi is equal to negative beta RC over R pi. In definition, what is Rn? How would it change if we had more resistors? What do you mean by more resistors?
All right, so in a lot of questions, I see that there is some like parallel resistors between R pi and R sig attached to ground.
Mm-hmm.
And I'm a little unsure of like how that would change Rn, because I don't know exactly what what is Rn measuring? Is it just measuring the total resistance on the left side, or can you explain that?
Yeah, so Rn, it really depends where you're measuring Rn. So you'll want to look at the circuit and the drawing that you're given. So here we see that Rn is at this like open dot. So it's measuring the, how we learned it is the resistance that's seen when you look at this point. So if you're at Rn and you're looking at the circuit in this way, what is the resistance that you see? So here we see this one resistor. If this dot, if this Rn was drawn, I'll draw it on, I'll undo it. If we draw our Rn right here, so this dot is here, so we're looking in like that, we're gonna have R sig in series with R pi. That's the resistance that we're seeing. Whereas, let's say if you, like you were saying, you have, undo that real quick. Let's say, for example, you had another resistor in here and your Rn was outside of it. So like this, looking in, then you would have those two resistors in parallel. Kind of, I don't know if you saw our last question. I'm not sure if you were here for 7.33, but let me just go there. Here, our Rn, this was a MOSFET, but you can imagine that it's a BJT. Here, you had two resistors in parallel, and then you have your small signal here, or VGSs. So it really depends where your Rn is drawn. Is it after, before the resistors? And that's how you'll know which ones, which equation to use. Are they part of Rn? Are they not part of Rn?
All right, I understand now. Thank you very much.
Okay, perfect. Awesome. Let me, hello. What did I do? Oh, okay, I'm back. I don't know what happened there. Sorry about that. Okay, and I will undo. I'm not sure if it will undo. Okay, let me just erase this resistor I added here. Okay, that's V pi. All right, so overall, the last thing that we are finding is VO over V sig. So we have all of the equations we need for this, right? We have V pi over V sig, and we have VO over V pi. And from this, we get negative beta RC, R sig plus R pi. And this is also what in the question they ask us to verify, and we find that that is true. All right, so these are the questions that I have prepared for you. I have a Kahoot ready if you want to go to it. If you want to ask me anything else, I can definitely try to answer. I know the only other thing I have written down, which I just think is important for you guys to know, I'm not sure, is your exam open book? Do you have your notes? Yes, it is. Okay, perfect. So I think the only other big thing you guys have covered in the second half is your CMOS inverter, which shouldn't be too hard, especially if you have the notes. I remember I just had to have some of these things memorized, but if you have the notes, it's very helpful. But it's better to know it yourself a little bit, just because it's faster. I've noticed just because something is open book doesn't mean that you know, you don't want to be searching through your notes. You want to really know what you're doing, what you want to be finding. So the only thing is, for CMOS, obviously you want to know your different regions. You don't have to memorize the table of in what region, what is the which is the NMOS, PMOS in saturation or triode or whatever. So you don't have to have that memorized, but it's something that's very good to know. I think that's the only really thing you have for CMOS right now, right? You have finding what, they give you some values, you find what region you're in, what would, are they in saturation, are they in triode? I don't have a specific question for that, but if you guys want to ask anything about it, feel free. If not, we'll go to the Kahoot.
I just have a quick question before we move on, actually.
Sure.
You know, when you mentioned that there's the 2 equivalent circuits for BJTs, and depending
Yes.
on what inputs or what things they want you to look for, you choose the one that's best suited for that. What is the actual, like, do you know off the top of your head, like if they're looking for GM or whatever, use this? Like, is there an actual like quantitative way to determine that, or should we just be like, okay, let's just use this? If it doesn't work, we use the other one.
Okay, these are equations I have written down. I'm assuming you have them somewhere. Oh my God, what am I? Okay, for BJT, this is also something I recommend. Have a, you guys need it less. I had like a study sheet before my exam with the main things I needed to know for the BJTs and MOSFETs. And so this is part of what I had for BJT and AC analysis. Obviously, short your capacitors, deactivate your DC sources. And you have that R pi is beta over GM. GM is IC over VT, which is, I have IC over 25 millivolts because when I took it, we were told that VT is usually 25 millivolts, I guess, unless you're told otherwise. And RE, do I have RE anywhere? Is R pi over beta plus 1. So those are your two, so those are the equations you have for going between the two small signal circuits. So you have this one. Oh man, my drawing is terrible. Oops. IB. This is your C here. This is your B. This is your R pi. This is your V pi. And this is your E. And the second one you have is this, right? And for what I remember, this is your VBE. And I believe this is RE, correct? No, it's R pi. What is RE? I am not sure why I have RE and what that's used for.
RE is for the T model. So you're looking at like the, I think, hybrid pi model. And so like the T model, it's like, I can't really describe it. There's like photos of it like through our slides.
Oh, perfect.
But yeah, it's just a different type of model.
Okay. Yeah, so that's what you would be using RE for. And that's, so yeah, which model you use depends on what you know and what you're trying to find, I would say. Does that answer your question?
Yep, that's good. Thank you. Just use the one you have the most values for, I guess.
Yeah.
Okay.
Yeah. And I don't know if this applies, but maybe whichever one makes your analysis easier. But they're very similar, especially these ones. I forget what the T model looks like. But if you find that it's making it look, if it's making your analysis easier, you can use that one. But these two are basically the same, since they both have this dependent current source. Did we do any early effect questions? Sure. What do you mean by early effect? Early effect is when you have the RO, correct? It's when your lambda is not 1. Yes. So we did have that. In our last MOSFET question, actually, we were given VA. And if we're given VA, so VA isn't 0, it means that we have channel modulation. So we have an RO in our small signal. So let me show you here. So in part B, we were told that VA is 100. Let me just find the equations for you. Have them. Oh, where are they? Right. So yeah. So you have one. Where can I write this? Okay, I'll write it. I'll write it here. So you know that one. Oops. Why does it keep doing this? I just want. Okay. 1 over lambda is equal to VA, and your lambda is your channel modulation, right? So you found your RO, and you add your RO here. Is there a more specific question you want to ask about early effect? Do you mean like how it affects your circuit, or?
No, I think that's fine. Thank you.
Okay. Okay. Yeah. For BJT, it's also, again, if you had channel modulation, you would have RO in parallel as well. So it adds an extra resistance. It does make things a little trickier, less clean, but it's not terrible. Okay. Any more questions, or moving on to Kahoot? I'm not seeing any. So I am going to start the Kahoot. Let me just get it here. Okay. I'm going to stop sharing this. And here is the Kahoot code to join. I'll also share my screen. There we go. So for the new people that joined maybe after I said it, the winner of the Kahoot wins a $5 Amazon gift card. So we're at, yeah, I'll wait some more before we start. We're at 24. I believe we have around 30 people in the call. I'll wait another minute for anybody else who wants to join. There's 25 here. There's 30 people in the, 24 here. There's 30 people in the call. 2 of them are me, so I'm not counting those 2, but anybody else wants to join, this is your last opportunity to. Okay. All right. I am going to get started. Is anybody else still joining? I don't want to wait too long here. Oh, we're down to 26. Okay. All right. Okay. I am going to start the Kahoot now. You have around 10 to 20 to 30 seconds for each question. And I am starting it now. Okay, so it is metal oxide semiconductor FET. Looks like everybody got it right. That plate at least. Okay. Oh, there's something in the chat. Yes, so there are 10 to 20 to 30 seconds. So depending on which one. Some of them are shorter, some of them are faster, depending on what kind of question it is. So watch the timer. Okay, next. The input gate current of a FET is? Correct, it's negligible. That's why we put it as 0. Okay, next question. A current ratio of IC over IE is usually less than 1 and is called? Yes, it's called alpha. So it's the other ratio that we sometimes use but don't often use. But it does exist. We usually use beta. All right. Awesome. Good job, everybody. All right. That's the 4th question. To operate properly, transistors Base emitter junction must be forward biased with reverse bias applied to which junction? Yes, it's collector base. All right, next question. Oops. The MOSFET is almost ideal as a switching device because it consumes low power. Yeah, so that's why we usually use MOSFETs over BJTs. It's low power. Next question. So this is our sixth one. Which of these is a correct small signal equivalent circuit of a BJT?
Okay, sorry. I'm just gonna say, sorry. It was the placement of it was very weird because like the different circuits were in different spots. I'm just saying that. It was like I don't know how to
Like it was A, B,
yeah,
C, D for those two.
That's why
Okay.
I think a lot of people got messed up.
Oh, so they all thought, okay, I see. Yeah, sorry about that.
Tragic. Oh well.
All right. So, well, that's good though that most of you guys do know which one it is though. So, all right. So next question. All right, yeah, so there's 5 regions. Sometimes it looks like 4, but remember it is 5. The one in the middle is also a region. All right, next question, we have 2 more. So remember, there's facts about CMOS inverters, and then there's assumptions. So which one of these is a correct fact? Yeah, VN is VGS1. That is the correct one. All of these are actually really close to the facts, just a few things switched up. So for all multiple choice, always just be careful of trick questions. There's just a little thing that's different. Okay, last question. Oh. Yeah, so that's the correct one, and it looks like most of you guys know it. All right, so to our winners. All right, congratulations, John T. Thank you so much, guys, for playing. If you could, one sec, I need to mute this tab or I'm gonna go crazy. Okay. Can you please email, email, what am I saying? Can you please message me? You can do a direct message of your email and your name. That would be great. So of John T, so that we can send you the Amazon gift card. We'll just wait for that. I hope this was helpful to you guys. Thank you so much for coming, and let me know if you have any questions. And John T, please message me. I'm not sure if you have. I don't see it. Oh, perfect. Thank you so much. Do you have a, actually probably Gmail is fine. I'm gonna ask for uOttawa email, but I think Gmail is okay as well. Perfect. Awesome. Thank you so much, everyone, and have a great rest of your day. Good luck on the exam. Thank you. Thank you, everyone. Have a good night.